think it's going to be a linear transformation? Oh, hold it, I just messed up, sorry. Do you think it's going to be a linear transformation? Well, if I took a peek, I had something like t evaluated at, how about a p bar plus q bar?
Okay.
Let's see if the first linearity property, excuse me if I can speak. Let's see if the first linearity property holds. I think this is going to be nothing more than t evaluated on p sub naught plus p sub 1x plus p sub 2x squared. That's another name for p bar. Plus, I'll make up another name for q bar. And if I add these two factors together, don't I get this? You guys get to relax. I'm not going to try to trick you. Just truly is what I get. However, now that this is a single element of P2, I get to map it over. And to map it over, I guess I get this. Now, if I try to take my hands and force separation with the coefficients of all my p's and the q's, do I not truly just simply get this? And this? Oh, by the way, let me reassociate. Somebody give me another name for what you see inside the parentheses here. T evaluated at P bar plus T evaluated at. Yeah, I agree. So it seems to me the first linearity property does indeed hold with this transformation. Do you want to see the other linearity property or not?
Yeah.
There was a yes.
Yes.
I think to show the second linearity property, I'm going to take T evaluated C times P bar. Just see. In the long run, massaging it, see if I can make it look like this. I mean, that's the name of the game. So, let me put it to practice, showing my details. I think this T evaluated some constant times, oh, here's another name for P bar. But this is nothing more than T evaluated at, actually removing the underset of parentheses, this one element of P2, namely this, plus this, plus this. But in transforming this element P2, I get nothing more than the constant term, plus nothing more than CP1 times x, plus nothing more than CP2 times, okay, I'll change the name of this placeholder. But you gotta confess, this is nothing more than C times all this stuff. And if you take a peek, a careful peek, at what you see in my outer set of parentheses, what you see in my outer set of parentheses is nothing more than
T mapped over.
well, T valued at P bar. So I think even the second linearity property doesn't hold. And if I come in with example number 3 and cheat a little bit, stealing my previous example, but in my usual fashion, trying to slowly raise my level of complexity. Notice example number 2. I was goofy. This x squared and this x plus 1 quantity squared are merely placeholders. They're merely placeholders, nothing else. What about example number 3? I think this might be a little more tricky. So let's check it. Notice how in evaluating t at the sum, this is really just adding in the regular fashion of addition elements in P2. So I'll add these two p's together. I just did, nothing changes. The only thing that changes is when I actually transform the vector. So you guys, let me use my eraser. Since I'm actually transforming what you see in the outer set of parentheses, here's a transformation. Constant terms don't change, I'll keep it. X term does not change, I'll keep it. It's just that when it comes to the last entry, I get to add 1 to that coefficient. I think I get a P2 plus Q2 plus 1 times my x squared. So up to this stage of the game, would you guys agree everything's fine with my definition of my transformation? I just have to determine if it's a linear transformation. But to do this, do you guys think I can slide things down a little bit? I'm going to work from backwards on up. Let's look at the sum of these two transformed vectors. I think I get this. Doesn't that give me my p sub naught plus p sub 1x plus my p2 plus 1 times x squared? Transforming the second vector, the q bar, I think that's merely going to give me is that going to be a p, excuse me, I misspoke, darn it. I meant my q. Sub naught plus q sub 1 times x. Plus q2 increased by 1 times x squared. Now when I combine these together, I confess my constant term is the same as what I have above my head. I think the coefficient is above what in my head as well, equal. It's just that when it comes to the coefficient of x squared, doesn't it give me a p sub 2 plus q sub 2, oh shoot, plus 2. So I guess in the end, they're equal. I guess in the end, messing with the coefficient of x squared in the way I did with the definition of transformation does not allow me to keep the linearity properties. Are you there? Sort of.
Well, I mean, it's not like you're doing anything complicated. We're just doing the.
I'm not.
We're just proving the same. It's like when we were proving closure. Same process.
Yeah, I think it's very similar. Or just checking any set of axes, to be honest with you. Because I've traded these as properties of linear transformations, going back to the argument we had about the change of the difference between the word properties and the axioms.
But I feel like you're going to throw something at us very soon for the next minutes.
Functions.
With what?
Like
With functions.
Yeah.
Transformations.
All right, I'll try to throw you at functions. Hi, rates.
Yep. Beard of sorrow.
Well, that's not a function. That's a lot of functions.
It's a lot of it.
Well, that's a functional, actually.
Oh, 'cause
What's your hunch? What's your hunch?
Yes.
I think it's a safe hunch. After all, you know, addition in the integrand's position converts to addition of integrals. And constants of functions in the integrand's position allow me to pull the constants out. So I do think initially, just at a glance intuitively, this should satisfy my linear properties. But let's verify it. I think t evaluated f plus g, by definition of t, is nothing more than the integral of
f of x,
tell me every
F
symbol.
plus G.
Every symbol in detail.
f plus g of x,
Parentheses.
f plus g,
There it
and
is.
parentheses, parentheses x,
Close parentheses.
dx.
You know how I got good at this? Because math is such a precise language. When I was a university student, I worked for disability services, and they would have me go through a calc sequence sitting on calc classes and take notes for blind students. Do you see my point?
Yeah.
They're blind. They can't read my notes. So I got to go home, and I have to pull out a tape deck and literally read the lecture symbol by symbol into a tape deck. So it gives you really good practice.
Were they good at math?
What's that?
Were the kids you helped good at math?
I'm embarrassed to say I have no recollection. It's just been too long. I really. What's that?
How long ago was that?
You could ask my age.
Tangentially asking, right?
Well, you're 21, so.
So this is like last semester, right?
Now I can't concentrate. It was like 29 years ago. Now you got me depressed.
Is this just time to ask Mr. Valguy personal questions?
Are there more?
I got one.
What?
What's with the beard?
What's with the beard?
Yeah.
Just be different.
Cool
Tell my
people
wife
have
yes,
beards. I mean,
Okay, because I was just looking up something. There's a Jewish tradition that in the morning the men are not allowed to shave their beard for a month.
You're kidding.
Yeah. No, I'm not. I'm not kidding.
I didn't know that.
It's called Shiva.
Ah, no, I had no idea. No, I'm not there. So you guys, actually, let's play this game again. Symbol by symbol.
Parentheses X.
DX.
X.
Plus
DX.
G.
Oh,
Parentheses X. Close parentheses.
DX.
Bracket
put
around
that product
everything.
Bracket around it. Yeah, okay.
Very nice.
Equals integral from -1 to 1 f of x dx plus integral
Okay, you
from
guys are there.
-1.
Very nice. But you guys see my point. I'm just pushing you guys to show the bloody details.
Okay.
And in the end, I think this is nothing more than a transformation of f plus a transformation of g. I proved that very first linearity property. And I think to show the other linearity property holds is just as easy. T evaluated c times f is not, I said T evaluated, I said that correctly. Evaluated c times f is nothing more than the integral from -1 to 1 of this function right here, evaluated on x, with respect to x, which is the integral from -1 to 1 of c times f of x with respect to x, but now I can pull that nice nifty little constant coefficient outside the integrand symbol, and I'm left with the integral from -1 to 1 of stuff. And I think in the end that really is c times the transformation of that vector f. Therefore, which I have not been writing in the past example, sorry, therefore t is,
Is a linear transformation.
Is a linear
you had,
Is indeed a linear transformation.
and we prove what we're going to show. I agree. Yes, Chris.
So what do we do with that? What do we do with linear functions for transformation?
Ooh, what a good question. Now keep in mind, I've got some kind of transforming process going from one vector space to another. In a lot of instances like that, I really like to undo that transformation and go backwards. Just sort of like when it comes to functions, so often we have this great need to undo functions and look at the inverses, particularly with trigonometric functions. It becomes a very big deal in applications. Same thing holds here with transformations. I'm not talking about next semester when you transfer. I'm talking about, this or next week. I'll be undoing these transformations. But unfortunately, the transformations that I can undo are going to have some very special qualities, which I've not yet discussed.
So I was just noticing the other day, I was looking at the syllabus, we have like a month of no tests before our final.
Yeah.
Is the final going to be cumulative, or is it just going to be a bunch of new stuff? Cumulative with a bunch of new stuff? All right.
I know you guys, you got to consider this 16th class.
Yeah.
Didn't I put in the syllabus our finals on Friday?
Yeah.
For like a long time.
Friday the 13th.
Is it Friday the 13th?
Yeah.
Is it really?
Yeah, it's Friday the 13th.
But 13 is a prime number. It's got to be good.
That's the luckiest one.
Magic Earth.
Wait, when is Friday?
Huh?
What
The
Friday?
final exam is on
December
Friday the
13th.
13th.
Friday the 13th.
You know what? I don't know if you guys are aware of this, but many graduate schools require you to take classes, stuff like that, do research, but no matter how well you do in your classes, at the end of your program, you've got to take what they call comprehensive examinations, particularly in the sciences and math. And it doesn't matter how good of a student you are, if you don't pass your comps, you're out. And you usually can't take your credits to transfer. So it's like a loss of years of your life. And I remember I went into my abstract algebra comp on a Saturday for 4 hours, and the professor showed up an hour late. And so after a couple hours into the exam, he came in an hour early and said, "Come on, you guys, you're not finished now. You're not going to do anything significant. I want to go home." So, wow.
This is in grad school only?
Yeah.
Okay.
That's hard.
Yeah, they treat you like slaves. And you guys, I don't know if you're aware of this either. How many of you think of going to graduate school?
Not
few
for
of us. Well, I didn't mean math.
It's probably for computer engineering.
So you guys also might be aware that, when it comes to graduate school, they require you to know a foreign language. And I know when I went to graduate school, a lot of my peers had studied Spanish, and university said, "Forget it, we will not accept Spanish as a foreign language."
Because everyone does it.
No, because at least in mathematics, they didn't feel there's enough research in that language. And so you might find yourself restricted. So if you're interested in graduate school, you might want to look ahead, identify a school you're interested in, to see what the requirements are.
So what kind of languages? I mean,
German, French, and Russian.
Like if
French,
I-
German, Russian, Chinese.
I was thinking taking
Yeah,
Japanese.
Japanese.
Yeah, Japanese. Yeah.
That's
All right.
And
That's
Japan may be a
fun.
small country geographically, but in terms of scientific and mathematical knowledge in the past, particularly since World War II, it's been rather significant.
Yeah.
It's not a wasted language.
This is so much more advanced than us.
What's that?
They're so much more advanced than us.
Oh, there are disadvantages, trust me.
No, I was
They're-
making a joke.
Oh, okay.
International currency disadvantages there because their currency is like so much higher than the rest of the world. So when they like ship products out to like other countries, they lose a lot of money on it.
Another really big significance is we're so free here in terms of education.
Yeah.
You guys want to mess up your entire academic career in high school? Just trash it?
Yeah.
You can, and you can resurrect yourself. That's
Yeah.
typically not the case in other countries. Even very free countries like England.
Yeah.
You guys check this out. Suppose this is a linear transformation. I already know it holds the linear properties. Then I insist, when you look at the zero vector, this first vector space, it gets mapped to the corresponding zero element in the second vector space. That necessarily has to be true. To show you that it is true, take a peek at my transforming the zero element of the first vector space. Can I use that zero bar with a subscript v to designate this zero element of the first vector space? Isn't that the same thing as this?
Yes.
Isn't that the same thing as this? Because I assumed I've got a linear transformation. But I think the scalar times, look what's above my brace, everybody. That's an element in the vector space W. 0 times anything in the vector space labeled big W is going to be nothing more than the zero vector. And that second vector space that I got labeled big W. What? I'm trying to impress upon you, if I've got a linear transformation for free, the zero element of the first vector space gets sent to the zero element of the second vector space. Are you there?
No.
Oh, you don't like that.
Well, I'm just not there yet. How did you get to the last step? You have 0 times the transformation of the 0 vector in V.
But the transformation of the zero vector in V is the zero vector in W, right?
Yeah, but you pulled the zero out of the zero vector,
Yeah,
right?
the key here, Chris, check this out. That one linear property says T evaluated C times V bar is C times T of V bar.
I get that. But then the next step.
Listen to my choice of words. Look above this brace. That's a transformation of this vector. Let's pretend we don't know what it is. It's something in the second vector space. Ah, but shoot, whatever it is, multiply by 0, you're necessarily going to get the zero element in the second vector
Oh,
space.
I see. So multiplying any vector in the vector space W by the scalar 0 will always get you to the
Yes,
vector.
that's true in any vector space.
Okay.
But you guys, this looks subtle, it looks useless, it's a big deal. It really is. So keep in mind, the 0 in the first vector space always gets sent to the 0 in the second vector space if the transformation is a linear one. What if this happened? What if I had a whole collection collection of vectors in the first vector space getting mapped to 0 in the second vector space? What if there's a whole set of elements in the first space that get mapped over here? I got a special name for that set. I call it the kernel of my transformation. By the way, I'm assuming I got a linear transformation. By definition, the kernel of a linear transformation is a collection of vectors, the v-bars, in the first vector space such that they get transformed to the 0 element in the second vector space. And again, in English, I refer to that as a kernel of my linear transformation. So I think in erasing what I have shaded in here, I'm going to refer to the set as a kernel of T. I got another set I'd like to define very carefully for you. That would be the range of my transformation T. And the range of my transformation T is this. With my blue pen. Ooh, I lied. I meant to say, with my red pen, if you look at what everything in V gets being sent to, which may not be all of W, but this set right here, which is a collection of all transform vectors to the first vector space, is what I'm referring to as a range of T. Shoot, I need to attribute symbols to that. I guess what I'm really trying to say is this. It's a collection of all elements of the first vector, of the second vector space. All the transform elements from the first to get into the second, such that V bar range is over the vector space V. That'll be my working definition of the range of a transformation.
So if there is a vector in V, and you apply the transformation to it, and it sends you to the 0 vector in W, it is part of the kernel.
Yes, it is an element of the kernel.
There are really transformations where kernel T doesn't consist of just the 0 V.
There are. Those would be very special subclasses of linear transformation that I will refer to as one-to-one linear transformations. And I'm going to have to satisfy that quality, that only the 0 element in the first vector space gets set in 0 element in the second vector space if I'm going to be able to undo a linear transformation. If I'm going to be able to come up with an inverse one. Again, not in the distant future, I mean now. We're going to look at just that.
So just to clarify, the kernel is the set of all vectors in your vector space that become the 0 element in the second vector space.
Good. You might slip into the extra phrase, all the elements in the first vector space that become the 0 element in the second space.
Through your transformation, it becomes the 0
Yes.
element.
I agree. So everybody, I think the kernel and the range are subsets of V and W respectively. Or do you think they're stronger? Or do you think they're stronger?
Wait,
Yeah.
before you move on, I thought,
Yes.
so you can, when you're creating the transformation from one vector space to another, you pull a 0 out of the 0 vector. You can only do that for a 0 vector, pull a 0 out,
Yeah.
yes?
Yeah. After all, think about it.
But-
I can't say some V bar is equal to 0 times itself. That's not necessarily true. But I certainly can say the 0 element of the vector space V is 0 times itself. Only because of the very special quality that the 0 element really has in the set V.
But you define the 0 vector in the transform space as all vectors that you can pull a 0 out of then?
If you insist, it sounds like a redundant definition, but if you want to do that, you can.
Doesn't that mean that it's possible to have something that is in a vector space by having more than one 0 vector?
Oh, jeepers, yes. Absolutely. As a matter of fact, when it comes to vector space, the 0 element in either one of the vector spaces, the 0 element in any vector space has to be unique. I tried so hard this summer to create an honors project for this semester to show how crazy things get if you do not have the uniqueness of that 0 element. I failed. Just need more time to think about it. But yeah, good point. It has to be the case of 0 element's going to be unique. Oh, you guys, what was I just saying? I was saying, oh, instead of just simply saying, I got subsets, I got subspaces. Let's prove it. So there. Oh, I better be official. Let T from V to W be a linear transformation. Both this set and this set are subspaces of V and W respectively. For me to prove it, let's look at the kernel first. To show you that the kernel of a transformation is a subspace, number one, I got to show it's not empty. Is there anything in the kernel? Is there anything in the kernel?
Yeah.
What is it?
The zero is zero.
I agree. Now, let's just, you and I suppose, that U bar and V bar are in the kernel of a linear transformation. And let W be equal to U plus V. And let's see if W claims membership in my kernel. If I were to transform my W bar, wouldn't that give me the transformation of U bar plus V bar? Oh, wait. I didn't say that T was some kind of transformation. I said T was a very special transformation, a linear transformation. So I know that T valued U bar plus V bar is the sum of these transform vectors. But jeepers, that's just nothing more than 0 bar in W plus 0 bar in W, because U bar and V bar are assumed to be in the kernel. But that's going to be nothing more than 0 sub W. So clearly I got closure for addition in the kernel. I think just as easily you and I can suppose that U bar is in the kernel of my transformation and correspondingly K is in my collection of scalars. And let's go to let. How about a W bar? Be nothing more than C times U bar. Check out what happens when I transform W bar. If I can show you, the reader, this is nothing more than the corresponding 0 element in the second vector space, if I can show you that, then I've shown you that W bar is actually the kernel by the linear transformation. It's just that W has its alternative name. And it is just that. T is a linear transformation. I've got the second linearity property. It is the case that U bar is in the kernel of T, therefore T valued U bar is going to be the 0 element in the second vector space. But that's just simply going to give me the 0 element in the second vector space. I just proven that the kernel is going to be a subspace of T.
I'm sorry,
Don't
I
apologize.
remember in our vector space unit, we were talking about when we defined what the 0 bar was, we only defined it as the additive inverse.
Yes.
We never talked about what happens when you multiply a 0 vector by a scalar. Or graphs on different graphs.
No, you've got a good point. The fact that 0 times the 0 element is going to give you the 0 element right back is actually a consequence of all the axes we have in a vector space. It's got to be the case that that's true if the other axes are going to be holding.
Okay.
And you can prove that from the axes.
So I'll just look through the axes again, I'll see.
And yeah, see if you can prove it. You can't pull through it in class. What about the range? Is there anything in the range? I asked, is there anything in the range?
Yes.
What?
Because, it's, well, we defined the vector space to be, oh, alright, I'm sorry, let me start over. We defined V to be vector space, and the vector space gives you has to be non-empty. And so if there is a range, then it's, I'm sorry, I'm not sure where I'm going with this.
No, you're close.
Okay.
You said, look at the vector space V.
Yeah.
As a vector space, it can't be empty. At minimum, it has to have what in it? 0 element. Oh, but shoot, if T's a linear transformation, if it free says 0 element to... If T's a linear transformation, since it's 0 element V to
0
0 in W, oh shoot, that means there's something in W, something in the range, I should say. Good, I agree. What about closure for addition? Then doesn't, if I let, I don't know, I'm running out of letters, Y bar be equal to W bar plus Z bar. Is there an element in the first vector space that gets transformed to Y bar?
closure under addition, right? Oh, we're proving it, right?
Well, we have closure and addition in the vector spaces, but I'm restricting myself to a subset of the second vector space called range. Anybody? Michael?
I'm guessing it would depend on how we define V of the rest of the vector space.
You know, I really want to finish this argument for any vector space V, no matter what it looks like, no matter what its characteristics are. You guys haven't been this lazy. Y bar is equal to this plus this. But W bar and Z bar are assumed to be in the range of my transformation, which means there exists a U bar and a V bar such that U bar transform is W bar, such that V bar transform is Z bar for some U bar and V bar in my vector space V bar. But jeepers, this is nothing more than the transformation of U bar plus V bar. Well, because T is a linear transformation. But wait. The first vector space is a vector space. I've got closure under addition. So I think U bar plus V bar is going to be something. Oh shoot, you guys, look what I just did. I shown you that Y bar, the sum of these two B's, is expressed as a transformation of some vector in the first vector space. We're out of time. I can easily show scalar closure as well, just as easily. Don't you feel getting more sophisticated?
I feel like you rely on the vector as a linear
A lot.
So if this wasn't linear transformation, we'd never guarantee closure.
Correct. I agree completely. As a matter of fact, I don't even know it would be worthwhile to talk about the kernel. So I think the fact that I've got a linear transformation is openly important. You'll see all my proofs, I'm using those linear, some of the linear properties. Yes, can I talk a little more before I send you off with homework?
Yeah,
Is that okay? We can take a night off.
that'd be great.
All right.
Gotta go to the hospital. My sister's having a baby right now.
Oh, I thought you were joking about the.
No, I'm not joking at all.